Krakatoa, Pompeii, Vesuvius, Mount St. Noggins. Some ancient eruptions are so infamous that they literally made the newsprint. But it can be tough to say just how big these events were until now. Hi, it's me and this is my channel. In the last few decades, we've gotten a lot better at measuring the magnitude of volcanic eruptions, which has helped scientists paint a clearer picture of how volcanism has shaped our planet over the past several million years. And that includes painting a clearer picture of some famous historical eruptions. We know about them because they happened in places where people lived, leaving behind written records or other traces of their devastation. And we can study the layers of ash they left behind in the soil to figure out how tall the eruption column got and how far the ash fell. But there's another way to tell just how explosive an ancient eruption was by studying the scars they left on the land around them. It's called the Volcanic Explosivity Index, or the VEI. It basically describes the scale of an eruption based on the volume of material ejected, which is usually pretty closely tied to how high the eruption column got. The index was developed in 1982 by a volcanologist named Newhall, and today it's used by scientists all over the world to help describe the relative explosivity of different eruptions. It's basically a really helpful tool for communicating to policymakers and the general public about the severity of an eruption. The way it works is simple. There are 8 numbered levels on the scale, ranging from 0 to 8. Each level represents a 10x increase in the volume of material ejected during an eruption. So, going up one level means 10 times more material was sent airborne. As an example, a level 2 eruption might send about 100,500,000 cubic yards of material into the air, while a level 3 would send 10 times that much, 1,500,000 cubic yards. There's also a half step between each number level, but for simplicity's sake, we're not going to talk about those here. In order to determine an eruption's VEI, you need to measure the volume of material ejected. But since most of the eruptions we want to study happened before the advent of modern geology, that isn't as easy as it sounds. You can't just go back in time and take a cube or anything. So instead, geologists look at things like historical accounts, archaeological evidence, and the thickness of the ash deposits to estimate the volume of material ejected. Once they have that number, they compare it to the thresholds for each level of the VEI. For instance, a level 4 eruption ejects between 1 billion and 10 billion cubic yards of material. So if your eruption is more than 1 billion but less than 10 billion, you know its VEI is at least 4. Level 4 eruptions also have distinctive geological features. They produce a crater that's between 1 and 3 miles across, and a debris flow that extends 5 to 15 miles from the base of the volcano. If your eruption left behind evidence of this, you know it was at least a level 4. So working backwards from the characteristics of the eruption deposit and working forwards from the estimated volume of material erupted, scientists can assign a VEI to historical eruptions that fits both the features in the surrounding landscape and the amount of material that was ejected. But even though this approach is good for historical eruptions, it comes with a huge caveat. You see, an eruption's VEI depends on the volume of material it ejects, which in turn depends on lots of things like the viscosity of the magma, how deeply the magma was rooted beneath the surface, and how efficiently gas bubbles could escape in the magma. All of these factors vary from eruption to eruption, meaning 2 eruptions with the same volume of material ejected may leave behind totally different deposits in the landscape. What this means is that the VEI isn't perfect. It's more of a rule of thumb guide to help us understand the relative severity of an eruption. Like, sure, an eruption that blasts 10 billion cubic yards of material into the air will probably be more severe than one that blasts 1 billion cubic yards into the air. But the details matter. A low-volume eruption with very viscous magma could carve out a very different sort of crater than a higher-volume eruption with runny magma. For instance, a 2021 study found that the nature of the deposits left behind after an eruption might make it hard to distinguish between a level 3 and a level 4 eruption. And that's just one example of how applying the VEI to ancient eruptions can be complicated. but we're still able to use it to get a sense of how some famous historical eruptions stacked up against each other. Let's start with Krakatoa, the Indonesian island volcano that exploded in 1883. We know about it because it was so loud. Eyewitnesses described a massive explosion that happened in 3 stages and was heard more than 2,000 miles away. Ash fell as far as Australia, and the explosion is thought to have killed over 36,000 people. Scientists have estimated that the total volume of material ejected during the eruption was somewhere around 24 billion cubic yards. To put that in perspective, that's roughly the volume of a 1 mile wide by 3 mile long by 150-foot high rectangular prism. Now, depending on exactly how you measure it, that could fit into a level 6 or a level 7 of the VEI. So Krakatoa was one of the biggest eruptions in recorded human history. But what about Nova Rupta? It happened in 1912 in the remote Alaskan wilderness. That's why it wasn't in the news at the time. Locals only noticed the ash the day after the eruption, when the sky went dark and the air turned cold. The eruption column reached over 20 miles up through the atmosphere, and the blast was heard 500 miles away. It was estimated to have ejected between 3 and 4 billion cubic yards of material, so the VEI is somewhere between 5 and 6. Now let's go back in time a little further to Vesuvius. On August 24, 79 AD, the Roman city of Pompeii was buried by an eruption of Mount Vesuvius. Most people think of the destruction of Pompeii as the worst part of the eruption. But at the time, the death toll was probably pretty similar to the 1980 eruption of Mount St. Helens. Vesuvius ejected about 1.6 billion cubic yards of material during the eruption, making it a VEI 4.6. While this was enough to bury Pompeii, it didn't come close to burying the entire Roman peninsula. The city of Naples was only lightly coated in ash, and it was business as usual in Rome, which was about 150 miles away. But there are even older eruptions that had an even smaller impact on the human world. For example, the 1666 eruption of Ischia, another volcano near Naples, Italy, ejected about 37 million cubic yards of material, which gives it a VEI of 2. This is considered large compared to most historical eruptions, but small compared to the eruptions we've already talked about. And it's estimated that the 1980 eruption of Mount St. Helens ejected around 1.2 billion cubic yards of material, making it a VEI 5. That's a pretty typical range for eruptions that cause significant damage. But there's also a lot of variation in the impact an eruption can have on the world, even if it has the same VEI. Take, for example, the Laki eruption in Iceland in 1783. An estimated 25 billion cubic yards of material was ejected during this eruption. That puts it in the same ballpark as Krakatoa. But unlike Krakatoa, it didn't kill many people. In fact, most of the deaths associated with Laki resulted not from the eruption itself, but from the effects of the eruption. See, Laki is a fissure eruption. That means instead of coming from a single central vent, magma came up through a series of cracks in the Earth's surface. The lava flowed for hundreds of miles, and the gases released during the eruption caused widespread crop failure. Meanwhile, the 1912 eruption of Nova Rupta was so remote that it barely affected human activity, despite ejecting an estimated 3 to 4 billion cubic yards of material. And finally, we can compare the eruption of Mount Pinatubo in the Philippines in 1991 to the 1543 eruption of nearby Mount Taal. The Mount Pinatubo eruption was one of the most well-documented in history and the largest eruption of the 20th century. At a VEI of 6, it ejected about 2.4 billion cubic yards of material. Meanwhile, the 1543 eruption of Mount Taal was only a VEI 4, so it blasted about 6 times less material into the air. But the difference in impact was staggering. The 1991 eruption of Pinatubo killed more than 800 people and caused $850 million in damages. But the 1543 eruption of Taal killed more than 6,000 people and was the deadliest disaster in Philippine history. These examples show us that the VEI is a useful tool for comparing eruptions that happen in populated areas. When looking at the VEI, it's important to remember that it's not just about the size of the eruption, it's also about the location. Some eruptions that might seem small on the VEI scale can have global effects. For example, the 1815 eruption of Mount Tambora in Indonesia was only a VEI 6, but it's thought to be the largest eruption in recorded human history. Its impact on the global climate led to the year without a summer in 1816. On the other hand, the 1980 eruption of Mount St. Helens was a VEI 5 and is the deadliest eruption in US history. But it only ejected a fraction of the material that was involved in the 1815 eruption of Mount Tambora. So whether an eruption is recorded in history or buried deep in the geologic past, the VEI can help us quickly communicate the relative severity of an event. Thanks for watching this episode of SCI Show. If you want to learn more about how volcanoes work, check out the link in the description for a playlist with several episodes about different aspects of volcanism.